Thank you for your time and joining us a little bit early. We're excited that you're excited. We have here today Don Boomer, Senior Applications Engineer, and Richard Stockton, Applications Engineer and Trainer, along with myself, Adam J. Brass. I'm the Sales Director for our venue. We're bringing you a very special presentation today, and we're going to drill down on paddles versus the diversity antennas. Right, Don?
Yeah, something like
Awesome. Well, I want to let you know we like to keep it casual. Certainly throw your comments as we go into the question and answers, and Richard and myself will answer the best we can or call your question out at the end. You submitted a number of questions already, so we're going to call those out at the end. But without further ado, Don, please take it away.
Well, hopefully we have a lot of those questions inside the presentation here. Um, okay, so what we want to talk about is LPDA antennas and diversity. LPDAs, paddles, shark fin. So that's log periodic antennas, and they're quite common. So I guess the first thing we should answer is what is an antenna? And the answer is it's a transducer, right? It changes one form of energy into another form of energy. Transducers have a lot of properties in common. So a lot of these things that apply to antennas probably apply to speakers and microphones, some things you might be more familiar with. Physics tends to be the same everywhere, but we're just changing the direction of the conversion. So an antenna, we're taking electromagnetic waves out of the air and converting them into something electrical, which we can stick in a receiver and make a radio work. The typical antennas that you're likely to see for use with wireless microphones and in-ears, of course, are the whip antennas that come in the box with everything. There are helical antennas that are used for long distance, and they're particularly good for working with in-ear monitors because they don't have any polarization issues. We'll talk about that a little later. But in the center is your typical your typical paddle antenna, your LPDA. These are remarkably similar from every manufacturer because we have to make them for the radio wave frequencies that you intend to use. So there's some physics that say they got to be like this, and you got to honor the physics. You got to make it the way it is, the sizes and the distances and all that stuff. There are other kinds of antennas. They don't get used very much for wireless mics, but there are a number of other kinds of antennas. But this is what you're most likely to run into. So some of the good points about LPDA antennas, paddle antennas, is they have wide bandwidth. So if you've ever tried to replace the whip antenna that came with your wireless mic, they're sold in much tighter ranges. Generally speaking, you won't find one that would go all the way from 470 up to 608 or whatever, wherever you are. If you're someplace else out of North America and have higher frequencies, they don't do well when you try to do that. So you'll see you actually have to order in the range that you need to make that happen. They have gain because what we're doing is we're focusing energy in one direction. So we're taking that sphere of energy and we're breaking it in. We're sticking a megaphone in front of it. We're going to take that whole sphere and stick it out through the megaphone. So we're going to redirect the energy. We don't actually amplify it, but we redirect it to an area that we want, and hopefully try to move it out of an area that we don't want. They're simple to use because you don't do anything but plug them in. You don't have to trim. Well, generally speaking, there's probably some you could find, but generally speaking, just take them out of the box and plug them in. You don't have to trim lengths. You don't have to readjust distances. All that stuff is built in, just ready to go. And they have low SWR, which means, so when you push energy into a transducer, it pushes some back, right? 100% of the energy doesn't go down the wire into the transducer and get converted out to whatever it's doing, right? This happens with antennas. This happens with speakers, right? When your power amplifier sends 1,000 watts to your speaker pushes some of that back. It might push 5 or 10% of that back. It's called back EMF when we're down in the audio range, and it's SWR when we're talking about radios. But these antennas are very good. They're very efficient. That's really what this is sort of a measurement of efficiency. So when you have low SWR, and we generally try to keep low SWR for most things in the radio world means better than 2 to 1. So and they do that quite nicely. Other kinds of antennas, it depends what frequency, it depends where you are in their range, that kind of stuff. So these are really great antennas. This is how you make one. It's an array, right? So you probably know we can stack up speakers and make a line array. Well, we can stack up microphones and make a microphone array. Maybe you deal with some of those new conference room ones that can be digitally manipulated and focused into fields. So basically what you have, you can see the dark here is a bunch of different elements, right? And their size and their spacing determine what the frequencies are going to be. The light gray is the same bunch of elements on the back side, and they're wired out of phase, so they're sort of isolators. But anyway, these antennas combine constructively, right, as opposed to your antenna farm, right? So an antenna farm is if you have a whole bunch of receivers and you put their little whip antennas in each one of them and you got a dozen antennas sitting on your desk, or you've put all your radios in a rack and you've front mounted the antennas and you have a row of antennas. Well, you do create an array, but it's who knows what it's going to be. I mean, because the chances of you getting the math right are like nearly impossible. So it's going to make some kind of an array, but what you're going to find is that it's inconsistent. And so you're going to get, likely it's going to translate to, you're going to have hot and cold spots as you walk across your stage. The coverage won't be even. And of course that means if you just step over a foot, all of a sudden you drop out, probably, or possibly, I guess I should say. So this is what you see if you ever look at the circuit boards and everybody's looks exactly the same, and different shades of black. I don't know. They're very simple. Now I'm not talking, you're also going to find these paddle antennas that have amplifiers on them. And that's a whole other ball of worms. Most of the time that's not a good thing. There's a very few times that it is, but generally you want to avoid the ones that have amplifiers in them because they're going to make your signal quality worse. Okay, so the reason that we have all these different antennas is we have different patterns from them, and we need to know what we're going to cover. So for most of us, most times we're going to point an antenna at a stage full of people, and that's what we want to cover. So if we look at our antenna in the center here, if we have an Omni, if we're using the little whip antenna that they come with, it's picking up in all directions. An LPDA is roughly 120 degrees wide vertically, depending on how you think about it. So it spreads out. It's roughly 1/3 of the coverage of an Omni, which means you take those other 2/3 that would have been going backwards and you shove them into the part that's going forward, and that means you get more range comparatively. The ratio changes, right? So and then there's helical antennas, which are even typically very narrow, and you get even more range, but you don't get as much horizontal coverage. So it's just a matter of picking the right one for the right job. But generally speaking, I'm going to tell you that 98% of the time you probably don't need to use an Omni. A directional antenna is generally better because it's not picking up the noise that's behind it, right? That Omni is picking up everything inside that circle, and this is not exactly to scale, but where the LPDA is only picking up things in your direction of interest and on, things where your stage is. We're not picking up all the rest of the garbage that's behind you or something. So like if you were on a football field and you put it under the goalpost, you'd be picking up the football field, not the parking lot behind you, right? So that helps keep your noise level down, which is what ultimately keeps you on the air. Oh, there we go. How about that? I got a football field. So yeah, you can see how these work. Now, if you need to pick up the parking lot, that's the job for an Omni, right? When it's the right tool, it's the right tool. There's nothing wrong with an Omni. It's just people think, oh, I'll pick up everything. It's like, no, I don't want to pick up everything. That's why you pretty much all use cardioid microphones on a stage because you don't want to pick up the audience, right? So we got the same kind of a situation here. So we just need to think about what we need to cover, and then use the right antenna to cover that, and hopefully not cover anything that we don't need or want. That's the trade-off we're trying to achieve. So when you look at these, this would be like if we're looking top down, right? So if we're on top of this sphere, we're at the North Pole and we're looking down, and the arrow is pointing forward towards our stage. The amount of pickup varies. It lessens as you get farther and farther off axis, just like most things. You walk to the side of a speaker, you stop hearing it. Not entirely, but it gets weaker. So the same thing happens here. And generally, when we call out a pattern, the number of degrees of coverage, that we limit that at the 6 dB drop-off point. And you can see, the 6 dB drop-off point, is in here somewhere. It's still picking up other stuff behind it, but you see this is greatly reduced compared to the front. It's almost 18 dB lower in the back than it is in the front. So we're not picking up as much of the stuff in the back. These aren't perfect. We can't just take a knife and slice them off, but so this is generally what you're going to see. I should go back to this. So 120 degrees is about the rule of thumb for sight, for peripheral vision for human beings. So if you place your head, like if you were going to put this antenna on a wall, if you put your head at that spot on the wall and you look forward to where you're aiming it, what you can see is inside this field. Probably it's pretty close, right? So if you can't see it, you don't have a direct line to it. You may get it, it may bounce off of something, but that's not a very good way to operate, when you can avoid it. I would never plan a system that way. So, pretty easy. Just wherever you got your antenna, pretend that's a wall, put your head on it, look where you're aiming the antenna, and what you can see is what this antenna is going to cover. So let's talk about diversity a little bit. So diversity is something that they came up with years ago, which basically allows two antennas to go into your radio. The idea is that when you have two different antennas and you separate them, if one antenna goes bad, the other antenna probably doesn't go bad at the same time. And this is a very, very, very effective technique to keep you from dropping out. There's a bunch of different ways that they do this. These are the most common ways, where either your two antennas come into something that determines which one has the better signal, it switches to that one. If we're over here, I'm sorry, on the left, your two antennas come into something that some kind of logic that picks between the two of them. It sends out a signal into your radio, and then it goes on. Or there's what they call true diversity, and you got to watch. A lot of these things are marketing terms, but in these, you actually have two receivers. So the antenna comes in, goes into a receiver, goes into a receiver, and then the logic picks the higher quality audio and it switches to that one or the other one and then goes out. There are some other schemes. There's one that if you have digital wireless, you can use something called vector diversity, where they when you have digital modulation, you get kind of what they call the cliff effect, right? So digital things you notice, like your TV set, like it works and then it just stops. It doesn't degrade. It just goes until it falls off the cliff. And because of that, there's some manipulation you can do with digital signals to try to straighten the phase out so that they don't cancel. And we're going to talk about that in a minute. It only works on digital. It takes some time to do. So you're trading reliability for a little bit of latency. Your signal is going to be a little late because of that. Very tiny amount, but it all adds up when you're running into a digital board and then into powered speakers that have digital processing. You're adding all these latencies together. So just be aware of that. So sometimes people think, well, all right, now I got two antennas. Again, if this was my football field or a big room or something, I'm going to put one antenna on the east wall and point it across the room, and one antenna on the west wall and point it across the room. And you will get coverage in the entire room. But you've got to maintain a somewhat equal ratio of antenna A and antenna B for this for diversity to work, right? So again, if this was a football field and I had antennas under each goalpost, if I get down to and I don't know where, the 30-yard line, the 20-yard line, the 5-yard line, somewhere as I get close to that one antenna, it's so strong compared to the other antenna that I no longer, it doesn't make any sense to switch to the other one, right? So I'm going to get diversity. I've got two antennas, both picking up a very good signal, sort of in the center-ish of this, and I can't. It just depends on a million things. There's not a number I can give you. I can't say it's 5, 10, 20, 50. It's different every time you do it. But just be aware, this is not the way to do it. What you'd rather do is put your two antennas 6 to 10 feet apart on the same wall and shoot in the same direction. And this way you have diversity covering the whole field. So you may not have, in the other event, if that was a really big, if that was 6 football fields long, I probably wouldn't have coverage. But if it's something that'll fit within the pattern of your antennas, it's better to put them both on the same plane, on the same wall pointed at your stage. You don't want to put them in the corners of the room. You want to put them, if you could move both antennas to the corner of the room, that would be okay. You want to keep these two antennas 6 to 10 feet apart, right? That minimizes the interaction that happens because of magnetism when it's picking up a signal. So 6 to 10 feet apart, your antennas, is a better way to do it than 50 feet apart. 50 feet apart will get you more coverage, but it'll get you non-diversity or less diversity coverage. So you're trading one thing for another. That may be what you need to do in a situation, but just be aware that that's what's happening to you. So that would be good, splitting your two antennas apart, but what happens is we have to consider the phase of the signal, right? So when antennas are spread apart, they're not seeing the same radio wave at the same time. And sometimes that's a real problem. So there's a thing called polarization. So when your antenna is in the same plane, when you're transmitting antennas in the same plane as you're receiving, you get full transfer. But if one is 90 degrees to the other one, you lose 99% of the signal. So you can see, turn on the transmitter, when the antennas line up, there's enough power to light that light bulb, and as it turns, the power diminishes. So you've got a constantly diminishing signal. So diversity normally would just switch that over to the other antenna, and that probably works almost all the time, but not always. Because what's happening is your signal is going to bounce off everything, right? So your antenna is not only going to pick up your direct signal, but it's going to pick up all the bounces, hundreds, thousands, I don't know, lots of them, right? So here he is walking around. I'm holding the microphone vertically, but you can see it switching back and forth between A and B, even though I haven't changed the orientation of the antennas. And that's because it's reflecting. So if you watch a pool table and you watch the balls bounce, that's kind of what's happening. Every time it bounces off a surface, it flips polarity, right? So what happens is your A antenna and your B antenna each receive a whole bunch of waves, right? And they're out of time with each other a little bit because they've traveled different distances, right? Even at the speed of light, this makes a difference. So if you look at this as a top-down view, right? I'm on the ceiling looking down. It could be a wall view, but anyway, what's happening, I just need to turn those antennas flat, and this would work better in 3D, but sorry, I'm not there, guys. So what happens is, if you look at one of the antennas, one of the paddles there, it's receiving a direct signal, and it's receiving, we're just going to count one reflection. There's probably dozens or thousands of them, right? And because they arrive at different times, their waveforms don't line up. And if they're not perfectly in phase, they begin to subtract from each other. So, and then you have a second antenna placed some distance away, whether we're talking 6 inches or 6 feet, there's some distance involved. And so it's going to see a different signal, right? So when both of these signals get down to the switching component in your diversity receiver, neither of them may be good enough to make your radio work, right? You're going to get polarization crossfade dropouts is what they're caused. And that's because you have distance between two antennas. Nothing wrong with the antennas, but because you have distance, it's just like, they're hearing echoes, and you got to try to figure out what it is. And when you put the two of them together, they might cancel each other out. So at RF Venue, this is why we started the company. We developed a solution for this. And what we did was to engineer a pair of antennas, a vertical and a horizontal antenna, and co-locate them in a single point in space. So this antenna, both its A side and its B side, see exactly the same signal phase-wise. Now, one might be stronger in amplitude than the other, and that's not much of a consideration, right? Because it's just going to switch over. But it's not gonna receive information that's harmful to the other side, because they're both seeing the same thing, right? There's no phase difference between the two signals, and that means you eliminate that polarization crossfade. That cannot happen with these antennas. So that's the advantage of our diversity fin, our diversity architectural, our omnidiversity, when that's the right thing, by co-locating these in a single point in space. So one of the questions I get asked, if I go back here, what if I have one of these antennas vertically and one of these antennas horizontally? And the answer is, you'll probably increase your odds, maybe by a factor of 2. But it still won't eliminate it, because who knows which way the bounces are coming. You might actually make it worse in some cases. In fact, you would actually make it worse in some cases. If we stop time, there's going to be a time where having them, two different directions is actually worse because they're separated. If they weren't separated, it would just simply be to one or the other. It's very simple. The antenna just takes care of it. But when you add the distance is what causes us the grief, right? Because that's phase. Phase is just means time. So there's no phase difference between these two antennas. So whatever signal you dump on them, they both see exactly the same signal. And then we're talking about amplitude changes based on polarization, but not the signal itself. So with that, I think that's what I had planned to show. We've got some questions there, Adam.
All right. Yes, absolutely. Let's run through those questions, shall we?
All
So
right.
let's see. So the first question is, can you explain cable gain loss and what do we do to account for that?
I think you mean cable loss, because cable doesn't have gain. Well, so every coax cable has loss over distance, right? Just like everything else does. Every piece of wire, you lose a little energy as it goes down the wire. You can look up the spec for that, and you'd like to avoid all the loss that you can, right? The longer you run any coax cable, the more loss it's going to have. Big cable doesn't have as much loss as little cable. Double shielded cable doesn't have as much loss as single shielded cable. So you're looking at all these things and you're going to lose some signal over length. But that's not the critical issue. The voltage, until it gets really, really, really bad, isn't the issue. The dynamic range, right? This is what we preach over and over and over again. The dynamic range, you have to have a strong signal compared to the noise that's in your room. So that's what's going to go in your antenna, and that's going to go down the wire, right? And until you get to the sensitivity limit of the radio, it's not really much of an issue, because you have to maintain 20 dB of dynamic range. Typically you're 30 or 40, right? That's where you'd like to be, and that's mostly where you are until somebody turns around or puts their hand over the antenna or something, and then it drops. Or you hit one of those null spots on your stage I was talking about, and it drops. As long as you have 20, you can afford cable loss. It doesn't bother you. The 20 is a go, no go, basically, threshold. As long as you're above the threshold, it doesn't matter if you're 2 dB or 20 dB above it, you're good to go, right? So as long as you don't lose too much. Now what happens is people tend to they think putting an amplifier on there is going to solve that problem. Well, it raises the voltage of the signal, but it raises the voltage of the noise. So it doesn't change the dynamic range. And in fact, it makes it at least a little bit worse, because every piece of electronics has got some distortion and, some signal loss, and, nothing's perfect. So there's always some degradation every time you run through everything, right? So you want to avoid that. And typically, strong signal is not as much of a problem. I'm sorry, strong signal is not a problem. Loss of signal is not as much of a problem as most people probably think it is, right? And in fact, professional guys that do, big shows, they're really pro-end guys, right? Guys that do arena level shows, typically pad their antennas. They actually put a pad and attenuate that signal, because they don't, as long as they've got what they need, any extra is actually harder kind of on the radio. Because if you turn it down, you're turning down the noise, right? So it's not that you're turning down the voltage. That would seem, if that's all we were talking about, that would be a problem. But it's the dynamic range, it's the noise. So if I turn the noise down, the sensitivity of the radio is kind of all figured in to the noise floor. So in extreme cases, you might have to use line amps, and they might work or they might not. But you should avoid them. Better to use better coax, spend the money for lower loss coax instead of the amplifier. And that's a better solution. That works most of the time. And if it's really long, then, RF over fiber is the solution. You can go miles with that. But that's kind of what that's about.
Excellent, Don. That's probably one of the most common questions we get on every one of these webinars. So we have some great information on our website on that as well.
Yeah.
Next question. Is an antenna distro system required with 2 or fewer mic systems in a university classroom environment?
Well, it's a trade-off. You can use a passive splitter. An active splitter probably has better isolation and better balance and all that kind of stuff. Do you need it? It depends where you are. If your classroom is out in the open in the middle of Times Square, that probably would be a benefit. It's more expensive. In a typical school classroom that you're not next to a nuclear reactor or something, you probably could just use 2x1 passive splitters. They work really well to a point, and then if you need performance beyond that point, then you got to go active.
Got it. Great. This is another common question. I need 1 or 2 wireless in another room that's not covered by the main antennas. Can I just extend or combine antennas?
So yes. So you might be lucky enough that it leaks through a wall if that just happens to work out. I would never design a system to do that, but sometimes you get enough leakage because you have enough dynamic range to start with. Even though the wall's blocking you, you get coverage. You can use that same splitter as a combiner. So you can put an antenna, actually your pair of antennas in room A and a second pair in room B. Just combine them. There's some signal loss when you do that, but that works well for most people. The thing that if you do it that way, the thing that you need to try to avoid is to not have a spot where your transmitter hits both antennas equally. Because again, they're going to be different distances. Now we got phase issues again. So if you're if you were in a metal lined room in room A and a metal lined room in 1B, that wouldn't happen. It wouldn't go through the walls. But so you want to try to avoid that. That's where so you can use attenuation. You can buy little passive blocks that plug in and lower the signal, because you don't need, if room A is huge, holds 1,500 people, and room B holds 50 people, we don't need the same amount of power in room B. So we could turn that down and avoid the leakage, the crosstalk. If you were doing audio, you'd think about it as crosstalk. So we want to minimize that, but it's very doable. Yeah.
Great. This is a great question, in my opinion. At what point, which kind of projects would you advise to have an external antenna? Minimum number of mics per project or venue size?
External, I'm not sure what
I
exactly.
think he's asking, when do you really need a remote antenna?
Well, it's almost always better, because if you put your, so if you have your antennas to a distro and then a rack full of receivers, and the antennas are mounted on your rack, typically your rack is going to be 3 or 4 or 5 feet up from the deck. That's not a good place to have antennas. Now, if you want to put your rack on a lift and lift it up so that the antennas are 8 feet in the air, so there's an advantage in having your antennas up above people's head height. That would be a reason. The other thing is if you've got them on your rack, you're probably using whips, and whips can work fine, but directional antennas almost always work better. They almost always fit people's needs better. Not always, but 95, 98% of people would be better off with directional antennas. So those aren't going to fit on your rack, so physically you can't do it. I don't know. It's a trade-off thing. If it works, you don't have anything that works, right? You can break every rule, and if it works, you're there. What do you care, right? And if you can break every rule, it's because you have that really high dynamic range. That's what's allowing you to do that.
Great. And for what it's worth, we see a lot of customers just installing a single antenna with a single wireless microphone. If the customer absolutely cannot have a dropout during their presentation, remote antenna will absolutely improve that performance. All right, so next question. I think it's the last one that you guys submitted, but we have some more questions that Richard is fielding right now. How can you minimize the production of third order harmonics and other parasitics in active antenna systems?
Level. I mean, the stronger the signal is, the more it pushes on the electronics and the more harmonics they generate, right? So, um, for one thing, I mean, like typically, there's a lot of moving parts, right? So if you have a paddle antenna that has an amplifier right on it, you can't get as close to that antenna as if you were to take that amplifier off that antenna and move it down 25 feet down the coax to the distro. You could hit that antenna with a stronger signal. So the stronger you hit that signal, the stronger signal you put into it, the more harmonics it generates. I mean, you could, if they were separate pieces, you could put bandpass filters, I guess, would help that a little bit. It's kind of clumsy, but that's what you would do. If they're built in, there's really nothing you can do. And the problem with these, as far as I know, every antenna, every paddle antenna that has a built-in amplifier is active. Even when you switch it to zero, you're running through the electronics, you're just not running with gain. So you're still going to get some garbage. So I guess, if you've got a paddle antenna with an amplifier on it and your microphone's 100 feet away, you're not going to have the same problem as if your microphone's 20 feet away or 10 feet away or 5 feet away. It's going to get worse as you get closer, because the signal is, picks up 6 dB every time you have the distance. So there's quite a difference in signal strength going into it as you get close.
Excellent.
But you're kind of stuck. I mean, it's kind of one of those, it is what it is, depending on where you are, and you're kind of stuck at that point.
Got it. Well, if there's any other questions, please enter them now. That's all we have time for today. I'm going to send you guys a feedback form. Let us know how we did and let us know what other training topics you'd like to see from RF Venue. Of course, we're always happy to help in any way, so you can email the team at info@rfvenue.com. All the applications engineers and myself, we see that email address, so please feel free to ask us any questions, RF related or product related. We're always happy to help. So thank you all for your time. We really appreciate it, and we're looking forward to seeing you on the next one. Thanks, Dawn. Thanks, Richard, and thanks
Thank you
everyone
all.
for your time.